Well, good morning, everyone. We're going to start today first by doing a exam review for exam three. Just remember the exam will post tonight at 12:01. I guess that's tomorrow, technically in the morning. Um, and um, Basically will be available till 1 o'clock on Saturday Saturday morning. With nominally the exam day is Friday. You can feel free to take it during that time if you wish. No pressure to do so, but we will, we will not have another lecture on Friday. Friday will be open for people to have time allotted to take the exam. Much like the last exam and the final exam will be, the exam consists of 30 multiple choice short answer question or true false questions. Very much look like the worksheets we've been using to prepare and keep people engaged with materials move along. Um, it consists of 30 questions in total, all online. You can be found in the worksheets in the quizzes section under with the same place as the worksheets. Again, will be open tonight, just after midnight, and should be much like you've seen before. So if you remember, really where we started with this latest specific component of the exam, we're talking about droughts and water resources. We talked a lot about three particular areas in the U.S. that I think are at the most risk from water shortages, and the most important ones we want to talk about here are California, the desert Southwest in general. So that's areas like Arizona, Nevada, um, and the Great Plains, the Central Plains, and the east of the Rocky Mountains. Um, and then where we spent a lot of time talking about, and it's such an important issue to the United States and the world in terms of the amount of food produced there, is actually the supply of water in California. So it's useful to know things for the exam, like where does California get most of its water from? The major sort of sources include melting snowpack, groundwater, and irrigation from the Colorado River. Of course, the big challenge here in California is that the snowpack is disappearing in light of climate change and drought, low number of El Nino years, removing the southwest monsoon, reducing snowpack, which is exacerbated by climate change. And as a result, the amount of water that can be received from irrigation from the Colorado River in Southern California, along the aqueducts and irrigation canals we've talked about with the Colorado River system, the deficits have to be made up by groundwater. The principal problems we talked about with groundwater, and I can't stress this enough, is that the groundwater doesn't recharge at a rate that's replenishable, and as a result, you see drawdown, subsidence, and a whole bevy of problems related to that, including irrigation ditches no longer working, broken infrastructure, and basically collapse of the alluvial sediments in that region by subsidence. So, specifically, what's the problem with each of these? Snowpack, the issue is that it's melting snowpack is disappearing in light of climate change and drought caused by change in the El Nino, La Nina patterns. Of course, groundwater withdrawals leading to water shortages and subsidence. And the reality is that the Colorado River is already dry, not making its way down to the Pacific Ocean, but it's under increasing demand of increasing populations across California, Arizona in particular, but most of the desert Southwest. So the sort of long-term cycle of water access in California area is pretty bleak, quite frankly. The big problem that exacerbates California in light of, on the backdrop of a dramatically increasing population is that, in light of the fact that El Ninos were pretty much non-existent between about 1995, 1996, and 2017, there's about a 20-year long drought where California received below average rainfall. And as you remember, I was talking about in class, there were major drawdowns of all the reservoirs. And there really wasn't a plan for where the water's going to come from. Luckily, 2017, I won't test you on the dates like this, don't worry. It was an El Nino year, and as a result of that El Nino year, 2017, almost catastrophically in terms of flooding and water-related damage, but replenished many of the reservoirs and the water capacity of the area. Although, because of the rate of that flooding, little of that contributed to recharging groundwater aquifers. So, the punchline here is that, since that, the last 3 years, we've gone to a major drought again. and the cycle is continuing on this year. So key things about the El Nino. El Nino typically leads to wetter conditions in the west and southwest, and in fact for much of the U.S. in general. Key aspects of that El Nino, of course, is that El Nino is related to warming of the central and eastern equatorial Pacific. So think off the coast of Chile, where that area becomes warmer, and as a result of the warming of that area, there's less upwelling of cold water. The warmer water is easier to evaporate, and you create moisture systems that drive rain into northern Mexico, the desert Southwest, and California. There is concern, even in El Nino years, that this may not be a great long-term solution to wet climate in that region or replenishing the water supplies in that region, because there's anticipation that increasing climate intensities will drive the weather patterns further to the north, and actually might be more raining in the north and South Dakota and Northern California than expected. So part of this drought in these years has been related to the fact that many of the storm systems move too far north, which are thought related to climate change. La Nina example is when there's cooling in the central and equatorial Pacific. Those typically lead to dry years in the desert Southwest and no rain in California. I have a question here. I'm feeling unconfident in presenting because it's not showing that my screen is being shared with all of you. And I want to make sure people can actually see what I'm pointing to. If anyone could chime in, just let me know if they're in fact seeing the Word document of the review sheet. I'd appreciate it. Okay, great, thank you. I'm not sure why it's not showing that it's being shared. The other source of water, the Colorado River, which of course only accounts for about 3% of the water discharge in rivers in the United States, but actually provides water to 40 million Americans, and provides the water for most of the agricultural activity in the Imperial Valley, is an incredibly important resource. It's a resource that's been fought over. There's a lot of political machinations. There's lawsuits that have been going on since the 40s, back and forth between states and within states, and between the U.S. and Mexico to sort of reallocate the water. But one of the key challenges here is that even though it's a small percentage of our discharge, it's a major component of our water supply for 40 million Americans, as well as for one of the most important food sources, where the Colorado River water irrigation accounts for more than 25% of all the food produced in the United States alone. The issue here to remember is that the largest users are California and Colorado, which actually corresponds to the populations of the state at the time when the compact was reached. The challenge here is that this actually has never been readjusted as populations changed. So at the time when California was heavily settled, but Nevada, Arizona, and New Mexico were not, this means that California has a disproportionate amount of the water, if you will. And as a result, even those other places have had increasing populations, they can't really utilize this resource to continue to expand their populations. Obviously, it's a perfect example of a situation where it ties back to the original concept of sustainability. We have to realize that we're making decisions that maybe aren't sustainable, and in reality, it's hard to see this being a sustainable resource for dramatic population growth in that area. So I already said this, but today we use every last drop of water that comes out of the Colorado River according to the proportions of the state populations back a century ago almost, and as a result, no water currently discharges to the Pacific Ocean. It is all used by the apportionments to U.S. and Mexico. Some general commentary about water. It's a rare chemical that contracts when it's chilled. I did cover this in class. It's one of the things about it. It's usually tasteless, odorless, at least it's supposed to be. And because of the fact it contracts when it's chilled, as I hope you already know, it's important because it allows the life to be sustained in things like lakes and rivers and stuff like that. Some facts about water resources themselves. These I think are important. I won't test you on 97.2, but the general idea is important to recognize, is that the vast majority of the world's water is locked in salt water in the oceans. It's not available for drinking. It's a huge reservoir of water, but it's not really useful in terms of thinking about it as a water resource. We alluded to the fact that there might be multiple volumes of oceans of water in the Earth's mantle, but also irrelevant to the conversation of where we're going to get water resources. Importantly, beyond that, the remaining nominally 3%, most of the fresh water that exists is in ice caps and glaciers. Many populations around the world, particularly in areas near the Himalayas or near the Andes, utilize seasonal melting of ice caps and glaciers as their drinking water resource. But by and large, most of the water that's not salt water is trapped in ice caps and glaciers and actually isn't available for drinking in general either. As a result, the two sources of water that are actually available for the majority of people to drink, and even in the case I just gave you in terms of the people living near the Himalayas and near the Andes, they're actually not drinking ice caps and glaciers. They're drinking meltwaters from ice caps and glaciers that get into either groundwater or surface water. So the punchline there is that groundwater and surface water are two major sources of water that can be consumed for drinking water resources around the world. The most usable drinking water is in groundwater. It's usually the highest quality. It's usually and it's actually the biggest volumetrically. Still, given the fact that it's much larger resource than surface water, and surface water can be easily contaminated by spills, sewage, nutrients, and a variety of different things we talked about. Surface water makes up 75% of the water supplies in the US and actually a larger percentage of water supplies around the world. The Ganges and Brahmaputra in India is an example of, major surface water that's used for drinking water supplies. So in essence, if you think about it, this implies, let's take the US alone, 75% of our population, including largely cities like Columbus as well, depend on surface water, even though it's the most vulnerable to contamination. And it's a much smaller resource than some of the other water resources like groundwater in the area. Guess jumping around here in terms of the way I presented initially, but remember that the solar radiation is the driver of the hydrologic cycle. The sun drives the hydrologic cycle. All the factors, including gradients, porosity, permeability, types of aquifers, their secondary effects. But most of the almost all the process is driven by solar radiation. Is what I'm trying to say. Once that solar radiation drives the hydrologic cycle, leads to cloud formation, transports water masses, and then eventually leads to precipitation. The fate of the water is controlled by one of three phenomena, and that is the water will either percolate through the soil and percolate into the ground, which is called groundwater recharge. A component of it can be evaporated directly or undergo transpiration, where plants take it up or release it through their stomata, called evapotranspiration. Or it can run off overland into streams and lakes and eventually lead to the oceans. Depends where you are, but in places like desert environments, evapotranspiration can be nearly 80%. In places like Ohio, it's actually about one third. Obviously, in the summertime, evapotranspiration when there's active crops can be higher, but in temperate, wet climates, they're about equal proportions. In dry climates, evapotranspiration can be really dominant. A little bit of like local Ohio relevance here. The Great Lakes, just north of us, we of course share a border with Lake Erie, is the largest freshwater system in the world, and that's quite a relevant water source for people living in this area. If you look at the most of the settling of the United States and Canada, I forget the number off the top of my head now, but it's a significant proportion of the population in the turn of the last century lived right around the Great Lakes for both countries in order to access this freshwater system. People used to implicitly think more about sustainability and build homes and businesses where there was access to water. Of course, that's changed a bit more as technologies have permitted us to go to the Southwest and build dams and things like that. On the topic of water usage, just like energy usage, has increased per capita in response to increasing global population. So there's really two incredibly important problems I can't stress enough, is that as we are in an inexorable climb to 10 billion people, every single one of them on average is actually using more water and more energy, as we'll get to later, than they used to. So water use is increasing, and that's both on mass and in a per capita basis. So how do we actually use water? The vast majority of water is used for agriculture or irrigation and power generation, or to basically generate steam to spin a turbine in some form or another. So we tend to spend a lot of time thinking about drinking water quality. The reality is most of the water is used for ag and for power generation. and which are obviously important for our modern lifestyles. But as a result of the fact of what I said earlier, power demands are increasing, food demands are increasing, water usage is getting more and more stressed. The key term that highlights this link between water and food, and water and energy, or the water energy nexus, or the water food nexus. Some people call it the water energy food nexus. I won't test you on the specifics of the difference of nuances of those terms, but the key thing here, particularly with the water energy nexus, is highlighting the inextricable link between water usage and power generation, which is the fact that even in scenarios where we are seeing increasing utilization of renewable energy resources that are lower carbon emitting, the challenge here is that they actually have a much larger water footprint than energy. People over time have made that balance between water and power, and of course that's our generation or your generation is going to face with reducing carbon dioxide, but which recognizing that's going to increase the amount of water that's used for many of these power generating supplies. So key thing is that, and this is important to remember, is that renewable energy resources release less CO2, but they typically consume much more water, and vice versa. In essence, coal and natural gas and gasoline, I'm not advocating for using them as opposed to renewables. I'm just making the point that they do actually consume much less water than some of the alternatives. As a good example of this, things like ethanol, biodiesel, or geothermal, which are some of the common, carbon negative or carbon neutral sources of energy, and renewable sources of energy, it's noted they consume significantly more volumes of water than fossil fuels, on the level of orders of magnitude more water consumed in these processes. So some of the general terminology of water resource, particularly in the environment, is an aquifer is a rock formation capable of producing water and supplying water at a usable rate. So the opposite of an aquifer is an aquitard, which is not capable of producing water and supplying water at a usable rate. What differentiates those two different categories is that aquifers typically have rocks that have enough pore space to have water stored in them. The amount of space between the grains actually tells you how much water can fit in a rock. Aquifers tend to have high porosity and good connectivity between the pore spaces. Aquitards tend to have low porosity and low connectivity between the pore spaces. So in terms of actually water flowing through that aquifer or that aquitard, the rates of groundwater flow are controlled by the gradient, how much of a difference there is between where the water is recharging and where it's discharging, or where the well is. So a mountain, if there are a lot of snowpack in California, wells down below that area often will have good hydraulic heads. So that's the hydraulic gradient is increased with increasing level of pressure and resistance to flow. And that resistance to flow is a function of how much space. More space makes it less resistant to flow, better flow, and better connectivity, which goes to the idea of permeability. Increasing connectivity allows water to flow better. So the terms I just introduced here, porosity is simply the amount of space in a rock, or the ratio of void space to rock volume, and permeability is the connectivity of those pore spaces in the rock itself. Some of the main types of aquifers, carbonate or karst aquifers. We have many of these in western Ohio and southern Ohio. These are carbonate landscapes that have been eroded and acidified, creating the cavernous caves. These tend to make very good aquifers for high yield and pretty good quality. Alluvial aquifers is another example. They are the largest. Think about the entire continent of India is nearly 90% of the country of India is covered by an alluvial aquifer. They're extremely large, but they tend to have very poor water quality and variable pumping. And the third type of aquifers are sedimentary or hard rock aquifers, which can be important supplies depending on groundwater flow rates. So there's porosity, they're fantastic. Things like sandstones can be great. Fractured rocks that have a lot of space that's there and connected can be fantastic. But in other situations that if there's no porosity, no permeability, those rocks can be aquitards themselves. So the key aspect of utilizing these aquifers, or some of the key aspects, drawdown is when groundwater is produced faster than it's replenished, faster than it can recharge. This is called groundwater overdraft, groundwater deficit, groundwater drawdown. You can use any of these terms. I won't test you on them, on the nuance of them. And basically, the biggest aspect of when that drawdown occurs, it eventually can lead to water shortages, subsidence, and loss of riparian zones in these areas. If you look at the desert Southwest in California, the amount of vegetation that's changed in that 20-year drought is insane. There's a lot of loss of riparian zones and vegetation period. Um, the water shortages can be acute when that that overdraft occurs, and most importantly, this can lead to major episodes of subsidence when that water is gone. That space can be lost by grains compacting themselves. We talked about specifically California, much of the Southwest, and the High Plains. Have extreme groundwater overdraft risks on many years. There's a net loss of water, and particularly in California and the High Plains area, there's major concerns about subsidence. We've already seen loss of riparian zones and water shortages. The important thing with the subsidence, as I alluded to before, is that where subsidence occurs, it's not often easy for that rock to sort of refill. Just adding the water doesn't allow it to expand, particularly if there's clay-rich minerals. They tend to compact, and that rock aquifer is basically lost forever. So, key thing here is any zones with overdraft have to recognize the need an alternative water strategy. Switching to drought-tolerant crops, alternative crops, ending agriculture, or basically, I've talked about the fact that there's a move towards trying to develop more tourism in those areas on the ranches with sort of dude ranches for tourism purposes, because there's no carrying capacity for the water in that area. So punchline to that is that agricultural and food crops are particularly important considerations for water usage. We highlighted before the amount of water used for different types of vegetables and meat and stuff like that. I won't of course test you on those numbers, but just recognize that particularly as you move up the food chain from plants to animals to the large animals such as cows, the water usage and the resulting amount of water budget for that food increases dramatically as well. I can promise you that this, switching over here to water quality, I can promise you that this definition, or both of these definitions, will be on the quiz. It's an important difference. Water quality is, we tend to think about water quality, we tend to think about pollution, the latter of these two definitions, but it's important to recognize that contamination means unsuitable water quality or diminished water quality. This just means the water is not good. Contamination can be natural, or it can be caused by human activities. Pollution is specific to human-induced decreases in water quality. So pollution is something like somebody spilled a chemical into the water. Contamination could result from pollution, but it also can be something like the example of high levels of arsenic being leached out of sediments into the aquifer, causing poor water quality. So various types of contamination. One of the things I want to highlight here is that the type of contamination, it depends on the intended use of the water. If you have a small amount of nitrate pollution, for example, or nitrate contamination generally, and you're going to use that water for an agricultural purpose, that may not be a problem, right? There are many areas, particularly in the coastal plain of the Gulf of Mexico, where there's major nitrate plumes, where nitrates migrating off, from the coastal aquifers into the Gulf of Mexico, and farmers in those areas have started pumping that water expressly for the purposes of harvesting nitrate contaminated or nitrate polluted groundwater and using it for irrigation, because there's not really any net problem with doing so. In essence, that water can be useful. But obviously, if that same nitrate contaminated or polluted water was tried to use for drinking water, it would cross thresholds and lead to some things like blue baby disease and stuff like that. So contamination has to be tied to the purpose the water is going to be used for. For perspective, just thinking about naturally occurring contamination, as I talked about this with India and Bangladesh and Vietnam, areas around the Himalayas, naturally occurring contamination causes health effects and toxicity in nominally 40% of the global population. So 40% of the people walking around planet Earth live predominantly in alluvial aquifers, or get their water in alluvial aquifers, and have net negative health impacts from exposure to naturally occurring contamination. In terms of the water quality contaminants or pollution, they can be sort of chemical, biological, or physical. There's a broad range of things that can influence water quality. The biological ones, we tend to think about pathogens. So this is an important point as a hint for the quiz. Notice that cholera, typhoid, hepatitis, dysentery are typically caused by biological pathogens. They're typically common in unfiltered water, and the biological pathogens are a major concern for things like dysentery, diarrhea, and other other health maladies, including things like tapeworm, stuff like that. Okay. Other biological form is oxygen demanding waste. Once you have these can be critters, if you want to think about it as algal blooms. These are where algae start to grow. They consume the water from the water, oxygen from the water supply, and as a result, they can reduce the amount of oxygen and lead to biological contamination. So your two main types of biological contaminants or pollutants, it can be either relate to either pathogens or to oxygen demanding waste that cause problems by removing water from the area. Algal blooms, when they have high oxygen demands, it leads to eutrophication from low oxygen levels, and eventually actually can lead to things like fish kills and loss of other species from that water. Chemical contaminants have a broad range. We talked about specifically nutrients. So that could be nitrate and phosphate contamination. We talked about this a lot in terms of the nutrients, nitrate and phosphate reaching things like the Great Lakes, diminishing water quality, and in any case, directly, in that case, catalyzing biological contamination through oxygen demanding waste. Metal contamination, these can be from naturally occurring things like arsenic or whatnot in Bangladesh, as an example, or it can be metal contamination from things like acid mine drainage, smelting or other industrial activities. Particularly in the coastal regions of the United States, the northeastern U.S., southeastern U.S., there are coal deposits that are present, and as a result, metal contamination from acid mine drainage is the single biggest impact to water quality, or the most impactful thing to water quality in terms of metals, nutrients from agriculture, and metals, sort of define the vast majority of contamination issues in the world. The third most important or most common type of chemical contamination are organic components. These can be organics can be naturally occurring organic components, such as things that break down from leaf litter or things like that, or more commonly, it can be synthetic organic compounds, which are generated for industrial activities and can cause a variety of health problems and lead to really poor water quality. Even though nutrients are chemicals, I want to just highlight here that nutrient contamination is a major class all to itself, and nutrient contamination commonly again includes nitrate and phosphates, both intentionally deposited on the surface of farms to stimulate agriculture and feed the world. So almost all of the primary source of nutrient contamination is agricultural runoff. The exceptions, a lot of folks. I did a study back when I was in graduate school in a suburban area of Rochester, New York, and most people love to blame all of the nutrient contamination agricultural runoff, but actually in localized areas, things like golf courses and people seeding their lawns and sort of suburban green space is another area where nutrient runoff is actually becoming important as an example of a non-point source of pollution. And basically, the second most important source of nutrient contamination is groundwater. This is not actually necessarily not led by agricultural activity in general, but agricultural runoff off the fields into the streams and the lakes is the most important source. But there's also nutrient contamination that's accumulated from water percolating into the ground that can cause major issues. And in addition to the domestic contamination I talked about with fertilizing lawns and golf courses and whatnot, another important source of nitrate contamination in particular is actually stemming from sewage discharge, septic tanks discharge, or septic grave fields where the nutrients from nitrate are mobilized really readily out of septic tanks. I already talked about this a little bit, but arsenic contamination alone influences more than 25% of the global population. There are other naturally occurring contaminants such as selenium and things like that, but manganese is an important one in the Appalachian Basin. But arsenic contamination is the biggest one that affects most people, and again, is entirely naturally occurring. Key aspect to that arsenic thing we talked about Bangladesh is that the contamination is arsenic released from volcanic and metamorphic sediments, typically recently eroded sediments. Once those sediments get buried deep enough that microbes have removed all the oxygen, in reducing low oxygen conditions, that arsenic becomes mobile and is exceedingly toxic. I don't think I'll test you on any mechanisms of that, but I'd definitely like you to remember that. might help you when you start to think about buying a home or installing a water well on a property, something like that. So again, the most common and largest source of metal contamination is acid mine drainage, leaching from mine tailings, the combustion of coal in general, and now also the storage ponds for fly ash or those combustion materials are now known to lead to major metal contamination, particularly areas like Tennessee, North Carolina, where a lot, Eastern Ohio, where a lot of the acid mine drainage occurred. They're now filling in those areas with coal combustion residue, which is creating a whole nother wave of metal contamination. Onto the topic of organics. Organic contamination, again, can be natural or anthropogenic. The key anthropogenic contaminants are things like benzene, toluene, xylene. You don't have to know those, I promise you. But BTEX is a common source of organic pollution, and most of these come from gasoline spills or actually leaks in tanks at gasoline stations. I don't think I ended up putting anything about this on the exam, but useful to know is that the common forms of organic contamination are usually classified as non-aqueous phase liquids, and they're either dense or light. If their density is greater than water, they're DNAPLs. If their density is larger than water, like benzene, toluene, and xylene, they're LNAPLs. I think I didn't put a question about that, so I'll just move on for the interest of time. And the last component there, biological, chemical, and physical. The physical contamination can be radiation. That again can be naturally occurring, uranium or thorium or potassium-rich rocks. It could be, particularly as we talked about in the United States, can be an issue with not actually having, with development of landfills that store radioactive waste. We haven't done that here, which we'll talk about in a minute. But low levels of this radiation can leak out from industrial activity, from hospitals that are using them as tracers, the industry that uses as tracers. But the most common source of radiation is actually landfills. It doesn't necessarily have high ionizing radiation levels, but radiation, people don't forget that we use things like radium and tritium and stuff like that in a lot of applications, exit signs, for example, and a lot of glow-in-the-dark watches have very low amounts of, at least they used to have radium. Now, most of them now use tritium. And that radiation is often dumped in a landfill and can actually be mobilized out. And then another really big one that's a physical process is sludge. That can be typically sewage sludge, or it can be organic waste such as leaf litter, trees. It can cause contamination. Often, important thing to remember here with sludge is that it can have a feedbacks between oxygen demanding waste and also chemical waste. But it's the physical waste itself also causes problems for water. And another aspect of water contamination, another aspect of sludge, is actually related to things like the coal, fly ash, and coal combustion residue storage ponds and lakes, which that material can build up, and when they are breached, as we showed you earlier, can cause an incredible amount of contamination to water quality. So often the sludge is stored in retention ponds. The thing is that these fail not that infrequently, unfortunately, and when they fail, they're pretty catastrophic. But most importantly, they commonly leak small amounts of contaminants out of the storage ponds. It's not a very efficient way to store waste like this. Similar to the mining site we showed you, the other aspect is that there's often these sludge retention ponds can be accessed by birds or wildlife who can consume these materials and lead to major problems. I think in the end, I didn't put much material about landfills on the exam, but the concept of landfills are an important thing. No one thinks about wanting a landfill near them. No one thinks about the value of a landfill, but they're probably some of the most cutting edge civil and environmental engineering and hydrogeology. They're incredibly important for actually preventing us from interacting with our waste products. And basically, it's an area where there's been a lot of improvement in strategy over the last few years from the episodes of things like the Love Canal and other landfills that allowed, we used to just think we'd put it in a steel drum and bury it in the ground, that'd be fine. And now, of course, we know the legacy of that is that it gets out, causes a lot of contamination. So particularly, storage of radioactive things, metals, and organics is a major issue. And landfill strategies have improved immensely. Nowadays, most landfills have a multi, double clay liners, multiple layers of clay and intermittent porous rock, where they can use the clay. It has low porosity, low permeability to prevent fluid flow from occurring, and then have an area of rapid fluid flow with high porosity and high permeability, often gravel or sand, where they can flush water through and clean this mess up when it's lost, when it breaches the system. Particularly, this landfill issue has become a major issue in nuclear power. Your generation will absolutely have to deal with the fact that we've been storing nuclear waste on site from power generating stations for decades now, and we're going through a scenario where we need to find a place to put that, particularly as it becomes not a non-economical source of energy. Power plants are starting to shut down, and there needs to be a solution for this. And landfill strategies or subsurface waste storage is becoming a major issue, and that's why this accumulating on U.S. Various power plants isn't really a great solution to where this is going to go. So, example questions. I think we're wrapping up here. Example questions. What are the geologic units that supply water usable rate from the subsurface? Hopefully, you would all recognize that aquatards. Oops, that's actually the wrong thing. It's highlighted there, so forgive me for that. Aquifers is the answer for units that supply water usable rate. I'll correct that online, but I promise you things like the definitions of contamination and pollution will be on there. I'll stop talking now. And I'll send out a note about that wrong thing being highlighted. But does anyone have any specific questions for me? I know I didn't do a perfect job of explaining this, so hopefully it doesn't just mean everyone's fallen asleep. If there's any questions, I'll hang on here for a little while. Otherwise, that will conclude our exam review. And given we only have about 10 minutes, 10-15 minutes left, I will pick up with fossil fuels on Monday rather than trying to cram that in before we stop. So good luck with the exam. I don't envision any problems. Feel free to start at your convenience after this evening. Hope everybody has a great week, and talk to you on Monday.